I wanted to make a video practicing using our constant acceleration kinematics equations. Now this is something that maybe you have experience with and you don't need this, and that's fine, but I wanted to do this for the people who maybe feel like they could use a little bit of some practice with this stuff. And so let's go ahead and look at a pretty simple example here. Suppose I start from rest in a tractor with acceleration of 10 meters per second squared. How fast am I going in 3 seconds? How fast have I gone in 3 seconds? Or how far have I gone in 3 seconds? So this is a kind of a standard style question. And so I just want to kind of go through my process for this and just kind of go through my steps. So the first step is I set up my coordinate system. So in this case here, there's my tractor. Again, I almost always have things start at 0 position, and the positive x direction goes this way, which is the way that it's traveling in. So my second step is to look at the question and figure out what constants we can get from there. Sometimes you get a lot of them, sometimes you can only get a few, sometimes they're really easy to see, sometimes they're hidden. It just takes a lot of practice. But I like to go through and just sort of figure those out. So the first thing is I'm going to say my initial position is 0. I sort of set that up myself. The initial velocity is 0. And so it's sort of implied here when it says, suppose I start in a tractor with acceleration of 10 meters per second squared. So this is kind of an example of one where that's a little bit hidden, and my acceleration is 10 meters per second squared. And so the last thing is we set up our equation. So here's one of our kinematics equations. And so here I take my constants that we just sort of set up. And so I literally, when I'm doing these, I make a little chart to the side with my constants. And so this is 0, and my equation looks like this here. That's my position equation. And then my velocity equation is going to look like this right here. And so in this case, my two equations look like this. And so at this point, this one's not too bad. We know that we're supposed to find these two things after 3 seconds, and so at this point I'm ready to plug in the time and kind of move on from there. So how fast am I going in 3 seconds? I plug in my 3 seconds and I get 30 meters per second. Hopefully that makes sense. The acceleration is 10 meters per second squared, so every second you're adding 10 meters per second on and you get 30 near the end. And then for the distance, it's this equation here with the t squared. And so I plug in and take the 3 squared and get 45 meters. And so that would be, again, basically this is like sort of the most fundamental version of one of these you can do, just to kind of get us started and kind of see the process a little bit better. So we'll move on, and one of situations where these equations are very useful is what we call freely falling bodies. And basically, close to the Earth's surface, every object has roughly the same acceleration. We call this acceleration g. Now, it's a little bit different depending on where you are, right? At the equator, it's 9.78. At the North Pole, it's 9.83. But they're all pretty close. And so we take sort of the average of that, which is 9.81 meters per second squared. We're going to talk more about gravity as we go on, but this is sort of where we're sort of starting right now. Is just as a given, the gravitational acceleration g is 9.81. And so let's look at the style of question we can do for a free falling body, which is, again, any object that's sort of flying through the air, and the only force acting on it is gravity. Now, realistically, a lot of times you'll have air resistance acting on these things. Now, in a lot of situations, air resistance can be neglected, and it doesn't turn out to be a sort of major problem. You'll still get a pretty close answer. And so that's what we're going to do. Unless we state otherwise, we're going to assume that any body, flying through the air is basically the only force acting on it is gravity. So here we got, suppose I throw a ball straight up with a speed of 30 meters per second. How long will it take the ball to reach its maximum height, and how high will the ball get? So let's go through and again do this. So the first step is set up my coordinate system. So here, just to be consistent, I'll make it the y direction. You don't really have to, but it's kind of nice. And we'll say going upwards is the positive direction. So that's kind of my first step. And so what's kind of nice is just to kind of sort of look at this for a second and sort of think about this. So I'm throwing this ball with a velocity of 30 meters per second. And so what we do is we start the time sort of once I let go with my hand, and it's going at 30 meters per second. And so what we say is, well, g is 9.81 meters per second squared. I'm just going to approximate for right now and say that that's about 10 meters per second squared. That's pretty close. And so since it's going in the negative direction, right, g is pushing down, and so I think this is my g vector here. What it's doing is it's taking away 10 meters per second every second. So at 1 second, I start at 30, or I'm sorry, at 0 seconds, I start at 30. After 1 second, I'm down to 20 meters per second. At 2 seconds, I'm to 10 meters per second. And then at 3 seconds, I've reached v equals to 0. And so here's the height, my maximum height. So my maximum height will always be when the velocity is 0. And hopefully it makes sense that the acceleration is still negative g, right? So this ball is in the air. The Earth is still pulling on it. That hasn't changed. And so at the top of its path there, the velocity is 0 meters per second, and the acceleration hasn't changed. And now we approximated here, but still we got a time pretty close to 3 seconds. So we can actually, just by kind of thinking through this a little bit, without even using the equation, get a pretty good idea. But now let's try to be a little bit more precise with this here. And so we'll go through and use our equations. So the next step I always like to do is to determine our constants. And so here's our fancy equations. And so I'm going to call where the ball starts to be the initial position 0, which again is a nice thing to do. Just makes your life easier. And so in this problem here, again, we define the positive y as being upwards. And so we know that g is going down, but the initial velocity is 30 meters per second and has to be positive. And then our acceleration, as we've been saying, is negative g, negative 9.81 meters per second squared. Now this is one thing that trips people up a little bit. G, as it's defined, is a positive constant. Right now, in almost every case that we'll use it, it'll turn out to be pointing in the negative direction, so we'll make it negative. But the actual letter itself is defined as positive. And we could have defined our coordinate system the opposite way, and then g would have been positive. But sometimes people will see the g in the equation and plug in a negative 9.81. And whenever you see g, you always want to plug in positive 9.81. And it's sort of, the way I think about it is we tell the g whether to be positive or negative when we start our equation. And so when I set up my equations, then my two sort of basic kinematic equations will look like this here. So I've just plugged in my values. Here I plugged in the initial velocity, and here I've plugged in negative 9.81. And so now we're ready to use these to go through and solve for what we're looking for. So again, with my process, you set up the coordinate system, you find your constants, you find your equations, and then you say, okay, what am I looking for? What equation would be good to use? And so we want to know how high the ball will get. So how can we do this? Well, there's a couple of different ways we're going to do this. What do we know about the ball at the top of its path? Well, we just sort of discussed this. It'll have 0 velocities. This is going to be a really handy thing. We're going to use this on a lot of these free-falling body problems. It can be helpful. So we'll set the velocity equal to 0 and solve for t. So I take my velocity final equation, set it equal to 0, and I go through and solve for the time. And you can do this yourself, and I get 3.05 seconds. Now before we had said that it was about 3 seconds. Now this 0.05 is basically comes from the difference between 9.81 and 10. So we got a pretty good close approximation. But this is how you would do it to get sort of the official number, the more accurate number. And so now once we have that time, what we can do is plug it into our position equation and find what the height would be. So why don't you stop here and try this one. So I throw a ball straight up with a speed of 30 meters per second. How high will the ball get from where I let it go? Okay, so hopefully you had a chance to do this, and you got 45.9. So I'm going to go through two different ways to do that. So we just went through and determined that the time to reach the maximum height is 3.05 seconds. So at this point, one nice way to do it is to just plug right in for that time final right here. And so you plug in that time, and you come out with that 45.9. Now, because we had done that intermediate step already, it's pretty easy to do that. But this is a good example, too, of the other equation that we can sometimes use, which is this guy right here. And you want to get, good at remembering to use this one because it can save you time. Like, for instance, for this problem here, you could have actually gotten the answer for this one in one step. And so for that stage, again, the steps here are sort of figuring out your coordinate system, find what your constants are, and build your equations. And so here, this would be my equation. And so in this case, I should technically call this delta x, delta y. But so what we do here is the same sort of idea. We know that the top part of the path, the maximum height, will be when the v final is 0. So I put 0 into here. The initial velocity is 30 meters per second, negative 9.81 for our g. We're finding the delta x, the change in distance. And I do that here, it's 45.9. And again, I should have used y here. My apologies for that. All right, so let's try one more example. So go ahead and give this one a go. Pause if you need to, and we can continue after. And so here we have a projectile fired vertically upward at time equals to 0, and we say that it reaches its maximum height at time equals to 10 seconds. What is the maximum height reached by the projectile? So this is an example of one where they don't give you a lot of information, but they give you enough to do it. And so this is, again, with these equations, there's a lot of problem solving here, and so it just, the idea is to kind of work through these steps and try to figure out the best way to do this. So go ahead and give this a go, and we'll talk about it. Okay, so hopefully you're able to get this answer here, B for this one here. And so let's just go through, again, our steps. So as usual, in a case like this, we'll just say that this is the positive y direction. And what do we have for our constants? So our constants are like this here. Okay, so we know that A is negative g. We'll just call this 0 because we always do. We don't know this one. Right? And so we're actually not given our initial velocity, but we know the time it takes to reach the top of its path is 10 seconds. And so what we can do is take these and develop a few of our equations. So for instance, our equations would look something kind of like this here. So it'd be v0 times t minus 1/2 gt squared, where again I got rid of the y0. And then my velocity will equal the initial velocity minus g times t. So again, we don't know this v sub 0, so that's what's kind of throwing us off here. And then our third equation, which is always nice just to kind of write out, is this guy here. So again, I don't know the v0 squared, but I know this is negative 2g times delta y. So what I'm going to do is I'm going to take this guy and use this. But again, this is our steps. We get the coordinate system, write out what we know, and develop our equations, and then sort of see what we got. And so right here, I can use this equation. So how would I use that equation? Well, so here's this guy. And I know that at time equals to 10 seconds, the velocity is 0, because that's when it reaches its maximum height. So again, that's a sort of super key piece of information that you'll use with many of these problems. And so this is 0 equals v0 minus g, and we know that that time is 10. And so once I rearrange my variables, I get that v0 equals g times t, or g times 10 meters per second. And when I multiply that out, I got 98.1 meters per second. And so now I've got that initial velocity, and I can go kind of a lot of different ways, but I think what I'll do is I'll go this way here. So this is v0 minus 2g delta y. And we're trying to find that delta y. And so again, at this point, we know that this is 0. This initial velocity we know is 98.1, and then minus 2g delta y. And so if I solve all this for delta y, I come out with v0 squared over 2g. And what I do is I plug in that initial velocity we just found, divided by 2 times 9.81, and this is where I get it's actually 490.5 meters, something like that. So again, that's just the example of these kind of problems. Yeah, so hopefully that helped. Thank you.